Toni, I'm with the YEF. And today's talk, just to give you a rough outline, will first start with basically how we got to scaling Ethereum. Because scaling Ethereum has been very quiet for a few years, if you remember. And then basically with 2024, people took scaling Ethereum way more seriously. And I want to start with first telling you how we got there. Like, how did we get to the point where people started scaling Ethereum again? And then focus the rest of my talk on the scaling roadmap. We don't dive deep into ePBS. I think Terence did a great job there, giving us an intro there already. But I want to mainly focus about block level access lists. As Drew already said, it's pronounced BALS and not the other way. And yeah, let's get started. So on this slide, you can see like the whole history of Ethereum's gas limit. It started very low, at the very beginning, 5K gas, you couldn't even do a single transaction. And then it slowly ramped up. You know, there was the DOS era, if some of you remember. And after the DOS era, core devs felt much more serious about increasing the throughput of Ethereum. And it started very slowly, if you look at the beginning of the chart. But then it slowly ramped up. And the most important update here was the London hard fork. Because the London hard fork gave us EAP 1559. And 1559 basically kept the average throughput the same. So the gas limit was already at 50 million by the time. But it allowed us to push it to 30 million. And you can see from London, basically until the end of this chart, the gas limit stayed where it is. You see, as soon as we did the merge, the average gas spent per day stabilized because of the 12-second slot time. But there was no real gas limit increase at this point. And this is where we are now. 2024, people get very hungry for scaling the gas limit. And then you can see this. We did an Ethereum Foundation AMA on Reddit. And there is this guy, Hong Kong Crypto, who asks, like, can we increase the gas limit? And Vitalik was very hesitant. He was like, yeah, we can do it. You know, it sounds reasonable, but we should be careful. And Vitalik was not alone. You can see Dankrad, who later became one of the biggest advocates for increasing the gas limit. Even Dankrad was still very careful because the 4844 hard fork, basically Denkun, I think, if I'm correct, was just around the corner. And Denkun increased the network throughput already by quite a lot. So in this chart, you can see this was right after we shipped Denkun. And the average throughput that basically the packet sent over the network increased dramatically. So this was the block as we knew it, and then suddenly we added blobs on top, and your bandwidth needed to increase basically. But there was a lot of headroom, so this was quite fine to do. Then there were other events that happened that caused us to slow down the whole thing a bit. For example, there was a Sepolia incident. Sepolia almost crashed. Geth forked off. There was a big block, over 10 megabytes, caused Geth to not accept the block over the engine API. And in the end, we had to basically come up with a quick solution to fix the network. This was live on mainnet. So if this was triggered on mainnet, we would have had big problems because Geth was at over 50% by the time. So this was a very bad situation. Also like calling for patience, basically. And then there were guys that had like a completely controversial take. Let me just call this one out. Like saying the gas limit should even decrease instead of increase because, of course, settlement layer and L2s are around the corner. You know, things changed a lot by the time. And I was not alone, right? People actually told me like, yeah, this is the right take. You're totally right. We should decrease the gas limit, go all in, cypherpunk, and so on. And yeah, it's very interesting to see, like, this is only like not even 2 years ago. And then the famous pump the gas era started with people like Paolo, Martin Koppermann from Gnosis. They were going on Twitter and basically pushing for a gas limit increase very hard. Mariano.eth eventually launched pumpthegas.org. And then it was basically the community's effort to really increase the gas limit. And you know how the gas limit works. It's voted by validators. So basically, there's no one who can stop them. The core devs can, of course, tell them what the right gas limit might be, but you cannot stop the validators from doing what they want, and that's quite nice. But then reality hit us hard because we discovered like we can't increase the gas limit over 39 million. So people were already in the process of pumping the gas limit, but in December 2024, we uncovered that if we would go beyond 39, then nodes would again fork off. And this would be a very bad consensus issue. So in the end, we had to find a solution. How can we increase the gas limit? Because the community wants to increase the gas limit without killing the network, basically. And in the end, there was this blog post I wrote, and we suggested, let's increase the gas limit, but let's only go to 36 million. And many of you might remember like this 36 million pump. This was how we started the whole journey of increasing the gas limit, going from 30 to 36 million, and thereby like taking a first step while fixing all the issues that we had with going higher. Justin was one of the first ones, very optimistic, very cool tweet here. He was basically one of the first validators that increased the gas limit. So this was in December 2024. And Justin then said he just increased the gas limit for his validators to 36. He was basically spearheading the 36 million, and then many people followed. And in the end, we managed to go from 30 million to 36 million after like 3 years of no increases, which was a very cool thing. Also on the technical side, we improved things a lot. So for example, we had gas limit.pigs that allowed us to track how many validators are already voting for the increased gas limit. Then the ETH PanOps team at the EF, they did a lot of research into how bigger blocks will affect the network. So we really focused on the gas limit a lot by the time and tried to figure out like what is the right approach there. Same for EAPs. This was basically one of the first EAPs that actually suggested to increase the gas limit. And by doing so, it was basically done by setting a default value in the clients. And this is a very effective way to increase the gas limit because as soon as you update your node and you don't change the default flags, you would just have this gas limit set. And over time, as you can see, we went from 36 to 45 to 60 million where we are today. And this is like the history so far. And everything we did so far was basically squeezing out everything we could from Ethereum clients. So there was no EAP that actually allowed us to increase the gas limit by freeing up time or introducing some more efficiency. It was basically just core devs squeezing out what they could from their code bases. And then there was a lot of slack that could be used in order to scale the gas limit from 30 million to 60 million. But the problem was basically how to continue from there on. So there's this problem oftentimes raised, right? Like, what do we do? Do we increase the gas limit and go all in gas limit scaling, compete with Solana and all those other chains that have way more throughput? Or do we focus on the crops, right? Crops is everywhere these days. And the trick here is actually quite simple. Yes, you just use your thumb and the pinky finger, and then you can get both. You can get the crops and you can get the scaling. And we needed some time to figure that out. And eventually, there was this renewed focus in the community, in the EF, at the core devs, and eventually we focused on, okay, let's make scaling the L1 a focus. The EF did the same. We had like 3 buckets, scale L1, scale L2, improve UX, and suddenly scaling the L1 was really on everyone's radar, and people took it super seriously. But then the question still remained, like, how can we move on? How can we get from 60 million, where we are today, to the next big gas limit increase? And for that, we actually need to be a little bit smarter than just pushing clients to improve their code bases. So there were many open questions, like, could we introduce some parallelization? Or what about the slack time in the slot, right? CKVMs, everyone has heard of CKVMs. They help a lot with scaling, but weren't around yet. And then optimize the networking, also a very obvious thing we can do. But in the end, what we decided for, of course, this is a very important slide here. One thing that was never on our on the agenda was just increasing the node requirement, because that would have been way too easy, and this would be the stupid thing, because of course just increasing the node requirements means we can scale very easily, but it also means we lose some of the nice properties that Ethereum has. So increasing the node requirements, even though very effectively, very simple, we didn't do that. So what we did instead, and this brings me basically to today, or already looking into the future, namely Glamsterdam. So for Glamsterdam, we scheduled 2 EAPs that were mainly focused on scaling. The first one on the CL side is ePBS 7732, and the second one is block level access list 7928. And for the rest of the talk, I will mainly focus on 7928. But if you're interested in 7732, just look at those 3 resources, basically the annotated specs, the EAP itself, and also POTUS did a very nice talk at DEF CON in Bangkok that I can very much recommend if you want to dive into the topic. So let's look at what we are going to get with Glamsterdam. And this is how a slot looks today. So the first time until second 0 to 4, we're basically busy with validating blocks and executing them, because in order to attest, you need to have your block fully executed, which means you need to finish executing your block within those few seconds. And then the rest of the slot is basically used for attestations, propagating them and aggregating them, such that the next proposer can include them in his block. And this is how it works today. Now, if we add block level access lists on top, which brings you parallelization, the picture looks like the following. You get like different threads executing your block, while we still have most of the time in the slot used for attestations and aggregations. And this is where ePBS comes into play. With ePBS, the block looks more like this. Let me see. We have first the block validation, attestation, aggregation, and so on. This stays the same. But then there is the payload validation. So the block and the payload are separated from each other so that you can basically have a lot of time for propagating the payload. So basically from second 9 to the beginning of the slot here, you can use to propagate the block, which gives us a lot of time on the network. And then at the latest, we would see the payload being revealed by the builder at the PTC or right before. And this is then the time we can use for execution. And if you now put BALs on top of ePBS, the picture looks like the following. And this is where we're going with Glamsterdam. Basically, as soon as the builder reveals the payload, we can execute it in parallel. And because there are probably some builders in the room, this might be very interesting for you, because when can you actually start building the next block? And this is right late in the slot, because the builder needs to get the block from the previous slot and then has to execute the block, and right then the builder can start building. So this is dramatically reduced from today. There will be way less time for building the block, but on the other hand, we get much more time for propagating the block. So this is like, to put things in perspective, this is the time builders have to build the block today, and this is how it looks like with ePBS. So the time for building the block will shrink quite dramatically, but talking to builders, I think they don't need so much time anyway, so this might be fine. And this brings me to the main topic here, ERP 7928, just giving you a rough outline how it works. There are 4 problems basically today. We have unknown dependencies, we don't know which transaction touches which part of the state. Then transactions touch the same state, so we can't parallelize them without knowing what the transaction will do. Dynamic access patterns, transaction can just branch into different directions based on the state. So even if you would execute a transaction early on, if you execute it after another transaction, it could do something completely different. So this makes it very hard. And the last point here is ERP 2930, which already introduced transaction access lists. They are optional, so you don't have to use them. And even if you would use them, you can't guarantee that your access list is actually correct, because sometimes what your transaction accesses just depends on where in the block it's placed. And this brought us EAP 7928, which the TLDR is introducing parallelism to Ethereum. So let's look at how block validation looks today. The first part of the block is basically downloading and propagation, and then you would switch between some I/O and between execution. So basically you would go to disk, you would load something, you would execute something, and then you realize, oh, I need some other value from disk. You go and read it, and so on. So this is like very inefficient. And at the end of execution, you would still have to calculate the post state root. So this is the last step because, of course, you need to put the post state root into the block header if you build a block, and this is the last thing you would do. And this is exactly the bottleneck here. It's sequential. We cannot parallelize this step until we do block level access list. So with block level access list, if you look carefully, the download time increases slightly. This is because the block level access list also needs to go over the wire. So it will mean we need more time for propagation. But at the same time, we get I/O, execution, and state root calculation in parallel. Looking at how transactions are executed today, this is exactly what I meant earlier with you execute, you go to disk, you execute, you go to disk, and so on. And you do that sequentially over all transactions. We are always assuming like a worst case block today, because many blocks, if you look at blocks today, many of the transactions are already parallelizable because they don't have conflicts with each other. But we are always dealing with worst case blocks that are not parallelizable. And this is an example of such a block. You have 4 transactions, they have to be executed sequentially. With block level access lists, the situation looks like the following. You would have one thread starting to prefetch state from disk. At the same time, you can already start executing. Everything that is not yet prefetched in your RAM, you would basically have to go to disk. But as soon as this prefetching process is finished, you don't need to go to disk anymore, and you can execute all transactions in parallel. It doesn't matter if they have conflicts with each other or not, because you will just be able, you could, in theory, execute the block bottom up. It would work because the block level access list gives you the state diffs between each transaction. So if you want to execute the last transaction, you would just have to check the block level access list. What is the state that you need to execute the last transaction? You generate that state, and then you could execute the last transaction. And this is the nice thing here, why we get this nice parallelization. Right, I already talked about this a bit. What is the block level access list? It's basically telling you what do I need from the state in that block. And you can then go and prefetch that. At the same time, it's also a state diff. So the block level access list, it's not only telling you what you need, but also what changes on your disk after each transaction. And this is the second point, is the even more important point here, because this is what gives you the parallelization in the end. Here is a nice graphic of what a block level access list looks like. It's basically this structure. You have like the block level access list, you have the accounts in there. Each account comes with those changes, and then you can look, for example, we have slot changes, which is the stuff that changes on your disk, basically every state that changes. And then within those, you have the storage key, and when the storage key is modified, and what the new value is after that transaction. So you can basically get a block state diff from it, but it's more granular. It's a post-transaction state diff, telling you exactly after each transaction what the state is going to be. And this gives us 4 very nice benefits. We can we can parallelize execution. So no matter how bad the transactions are ordered or how much conflicts there are, we can always get perfect parallelization. So it doesn't matter anymore if there are conflicts or not. The second thing is batch prefetch, which allows you to start prefetching everything from disk that you would need while already starting to execute. And this is very nice because you can just traverse your database, load everything up front, and then hopefully when it comes to executing the transaction, everything is already loaded. The third thing is parallel state root calculation. Because you have a complete state diff, you can start calculating the state root right from the beginning. So you don't need to execute any transaction. You just take the block level access list, you take the state the state from before the block, you apply the block level access list, and then you're ready to calculate the post state root. And the last thing is, this is like also very nice feature of it, it's just faster sync. Many of you might know snap sync. It's basically the standard method how we sync nodes today. And snap sync will also be massively improved and simplified with block level access lists. Going into the snap sync topic, there is a new EAP. It's 8.1.8.9, Snap v2, basically the second version of snap sync. And we don't have to go into the details here, but the nice thing is, instead of a very iterative process, that's how Snap v1 works today, you can just apply the block level access list. So you would download the block headers, that's part of the skeleton sync, then you would download the block bodies, you would execute them, and so on. And in the end, you would just apply the block level access list instead of asking nodes about try nodes. So whoever has implemented SnapSync or played around with it, you know how complicated it is and how error prone it is. And just applying the block level access list will be a massive simplification here. So getting to the end, what do BALs impact builders? This is like the central question here. Of course, builders will need to build the BALs, and they will not profit from the parallelization, because you cannot build it while profiting from it, right? But there is one thing where the block level access list might be beneficial for builders. This was the picture we had earlier, where basically you had only a little time, this small bar here in orange, to build the block. And with block level access lists, you can increase it slightly. So what builders can do, if they want to start building earlier, they could apply the state diff to their state, then start building earlier while validating the payload. So builders can also make use of parallelization by just applying the state diff, starting to build, and asynchronously validating the BAL. And this gives builders a little bit more time. I don't know if builders might actually need that time. This is probably to be figured out, and we will find that out as soon as ePBS is shipped. But this is definitely some of the nice things that block level access lists can also be used for. Right, and this brings me to the end of my talk. Thanks a lot. If you have any questions, feel free to reach out on Twitter, on Create a PR, anything. I'm happy to answer any questions. Thanks.
Whoa. You got mic, check. Extra run. We got time for one question while I set up for the next session. I'm going to cheat. 2 questions. One, how much can we increase the block gas limit due to this? And 2, is there any repricing of opcodes necessary as with parallelization?
Yeah, it's a good question. So it's not super clear how much we can increase the block gas limit. Of course, if you have like 8 cores, you get 8x execution parallelism. So in theory, 8x. But on the other hand, we add some more data to the block, which means the block will take longer to propagate. And also, if you have 8 cores, you cannot use all of them for execution, you know? You might be maintaining a mempool, you might need a core for your CL. So it's not super clear, like...
Okay, we have more cores than that.
Yeah, builders are fine. Builders have infinite numbers of cores, I think. But validators, you know, we cannot assume that validators can use 8 cores for execution. So I think right now the benchmarks look like you will get a 3 to 5x or something. This is like what we can then scale the gas limit. And ePBS will help further, because with ePBS we get more time for propagation. So the additional size from block level access lists becomes less of an issue. And then I would assume, like, we're at 60 million today. I think we can maybe push to 300 million by Amsterdam or after Amsterdam sometime.
Thank you.